Greetings, Panthers. Dr. Augustine here. Today we're going to talk about a technique called combustion analysis, which is used to determine an unknown organic compound, what the chemical formula for an unknown organic compound is. This comes from section 3.10, 3.10 intro, determining a chemical formula from experimental data. And you may have recalled in one of the prior videos, we talked about things like mass percent composition and how you can find the empirical formula from the mass percent composition. But we never talked about where those numbers come from. How do you find the mass percent composition, and where does that derive from? Well, it derives from this technique, this combustion analysis technique. So here's the idea. We've got a furnace of some sort, and the furnace will burn my sample up. I can flow oxygen into this furnace, so I put a sample inside of here, and I have a known mass of the sample. So let's call this M sample. So we've measured the mass of the sample before we start the experiment. We flow oxygen into this chamber, and there's a constant positive pressure of gas flowing across this reaction. What happens is this sample burns up, and the byproducts of the sample get pushed through this reaction system into two new structures which we've added. So before I do that, let's just talk about the generic form of a combustion reaction. So if we have some hydrocarbon or some organic molecule, let's say something like CXHYOZ, this really could be just about any organic compound, and if we react this with oxygen, the products of this will be carbon dioxide plus water. This is the generic form of a combustion reaction. It's a really important class of reactions in general chemistry, and you're going to run into these a whole lot more when you take your chemistry course. So this general form, some organic material plus oxygen yields CO2 plus water. So my byproducts of this reaction are carbon dioxide and water. So what we put on the back end of this reactor, the back end of the furnace, is a water absorber, something that will absorb the water that comes out, and a carbon dioxide absorber. And these are connected. These are all sealed up, connected, and then whatever stuff comes out of the back end comes out of the exhaust from the back end. So the type of measurements that we get are something like this. We have the mass initial of H2O, and then we can measure the mass after the reaction is completed, which we can call mass final of H2O. And we also have the mass initial of CO2 and the mass final of CO2. So what happens to these masses? Well, the mass should increase, right? As I'm generating water and carbon dioxide, they're getting absorbed in this special material that absorbs water and absorbs carbon dioxide. So if we measure the mass ahead of time, we have a certain mass, then after the reaction is complete, it should have gone up because we would have picked up some of this water in the water absorber and picked up some of this in the carbon dioxide absorber. Now, at this point, it's not really that important what the water absorber is or what the CO2 absorber is. The important thing is it's able to absorb all the products from this reaction. Okay? So, since we have these two quantities before and after, we can find the mass of H2O that comes from the reaction. That's equal to the mass final H2O minus the mass initial H2O. And the mass of CO2 is going to be equal to the mass final CO2 plus minus the mass initial CO2. Okay? So, we start with a known mass of our sample. We find experimentally the mass of water that's produced in this reaction. We also find the mass of CO2 that's produced in this reaction. Now, how does this help us? The way this helps us is as follows. Because we know the mass of H2O produced in the reaction, I can find the number of moles of H2O. And from the number of moles of H2O, I can find the number of moles of hydrogen. And for number of moles of hydrogen, I can find the mass of hydrogen. Now, it depends on the problem, depends on the type of problem you have. You may not need to find mass of hydrogen, you may only need moles. But the bottom line is, starting from mass of water, I can find moles of hydrogen. I can also find mass of hydrogen. And if you remember our other problem, when we were looking at empirical formulas, we need mole ratios in order to calculate this empirical formula, I would need to know the moles of carbon, the moles of hydrogen, and the moles of oxygen. So this is how we find moles of hydrogen. How do we find the moles of oxygen? Well, we start with, moles of carbon. We start with mass of CO2. From that, we convert to moles of CO2. Then we can find moles of carbon. And depending on the problem, we might need mass of carbon. Okay, so from the CO2 absorber, we found the mass of CO2. We can convert that into moles of CO2, we convert that into moles of carbon, and we convert that into a mass of carbon, depending on the problem, whether we need mass or not. If we need moles, that can go into carbon on this, in this equation. If we need mass, we can use the final mass that we've calculated. Okay, so again, starting from the mass of CO2 that we found from this experiment, we can either find the moles of carbon or we can find the mass of carbon, depending on how the problem is phrased. All right, so and then instead of talking about this generically, let's take a look at an actual problem. And this is one type of problem. There's potentially many other types of problems we could have. So here's the problem. We have some organic compound. It contains only carbon, hydrogen, and oxygen. A 4.24 milligram sample of the compound is completely burned in a furnace. So that, in other words, in my description before, this is mass of the sample. That's the initial mass. It produces 6.21 milligrams of CO2 and 2.54 milligrams of H2O. These are the things that are absorbed in those special absorbers. Okay, so in other words, 6.21 milligrams is my mass of CO2, and 2.54 milligrams is my mass of water. So this problem is asking for what is the mass percentage of each element in this compound. In other words, I want to know this at the end of the day. Percent carbon, percent hydrogen, and percent oxygen. Okay, you notice if you look at this problem carefully, we're not told anything specifically about the oxygen. And a lot of times these problems do not have anything about oxygen. So we're going to have to figure out the oxygen by process of elimination. If we can figure out the percent carbon and the percent hydrogen, then we should be able to figure out the percent oxygen. How can we do that? Well, we know that initially we're going to start with 100%, and if we subtract the percent carbon plus the percent hydrogen, that should equal to the percent oxygen that's left. All right, so the strategy in this, how do we attack this problem? Well, the first thing we want to do is find the mass of carbon. Then we want to find the mass of hydrogen, and then we want to calculate mass percent of the carbon and the hydrogen that we just found. And then our final step is going to be to calculate the oxygen percent, mass percent of oxygen. Okay, so this would be a good time if you want to stop this video and see if you can find the mass percent of carbon and the mass percent of hydrogen based on the hints I gave you earlier. If you come back in a second, we can actually do this calculation. Okay, so how do we find the mass of carbon? So the way we do this is we start with our mass of CO2, 6.21 milligrams CO2, and I want to get rid of that milligrams because I'd rather have it in grams so I can use the molar mass to get rid of that. So I'm going to say 10 to the minus 3 grams for every 1 milligram. Remember, this is a common mistake. Milli means 10 to the minus 3. That gets applied to the base unit. Okay? So I can cross off milligrams and I'll have grams of CO2. Now my next step is going to be, I want to find the number of moles. So 1 mole of CO2 for every 44.01 grams of CO2. Grams of CO2 is going to cancel grams of CO2. And now I'm going to say, and this is the key step, 1 mole of carbon for every 1 mole of CO2. Remember the mole ratio. Carbon and CO2 are in a 1-to-1 ratio. This would give me moles of carbon. My final step then, I'm going to take this answer and I'm going to say times 12.01 grams of carbon for every 1 mole of carbon. And then moles of carbon will cancel moles of carbon. That's all going to equal to 1.69 times 10 to the minus 3 grams carbon. Okay, that's the mass of carbon. Now let's find the mass of hydrogen. It's going to be the exact same type of problem. So the mass of hydrogen, we're going to start with the water, 2.54 milligrams of water times 10 to the minus 3 grams for every 1 milligram times 1 mole of H2O for every 18.01 grams H2O. I'm going to start canceling some units out. Milligrams cancels milligrams, grams cancels grams, times 2 moles of hydrogen for every 1 mole of H2O. So for every 1 water molecule, there are 2 hydrogen atoms. For every 1 mole of water, there are 2 moles of water, of hydrogens. And then to find the mass, I'm going to multiply it by the molar mass of hydrogen, 1.008 grams of hydrogen for every 1 mole of hydrogen. Note, this is not H2, this is H. Okay, because we're only interested in the hydrogen. This isn't molecular hydrogen, this is atomic hydrogen. So if I do this calculation, this comes out to be 2.85 times 10 to the minus 4 grams hydrogen. Okay, so we have done step 1, we found the mass of carbon. We found step 2, we found the mass of hydrogen. And one thing to understand is that this hydrogen and carbon could only have come from my hydrocarbon. Remember, I have oxygen flowing into this system. There's no other source of carbon and hydrogen. So everything, all the carbon has to have been absorbed in the CO2 or converted into CO2, and all the hydrogen is in the water. That's why we can get away with this. So we found the grams of carbon. We've also found the grams of hydrogen. Our next step is to calculate the mass percent of carbon and hydrogen. So the mass percent of carbon is going to be equal to 1.69 times 10 to the minus 3 grams carbon divided by, now we need the mass, but the mass is actually my starting mass, 4.24 milligrams of sample. It's not these numbers here. These include oxygen that have been picked up. It's the starting mass of the sample. So it's going to be something like this. 4.24 milligrams times 10 to the minus 3 grams for every 1 milligram. And this whole thing we need to multiply by 100% in order to give me percents. And this comes out to be 39.9% is carbon. Likewise, the mass percent of hydrogen is equal to 2.85 times 10 to the minus 4 grams divided by this same factor, 4.24 milligrams times 10 to the minus 3 grams for every 1 milligram. That whole thing times 100%. So this comes out to be 6.72% of hydrogen. Okay, so we're looking for the mass percent of each element. Well, so far we have found the mass percent of carbon. We've also found the mass percent of hydrogen. How do we find the mass percent of oxygen? The way we do that is we recognize that the percent of oxygen is going to equal to 100 minus 39.9 plus 6.72. Those are the percentages of carbon and hydrogen. And that is going to equal to 53.4% oxygen. Okay, so now I have found percent carbon, percent hydrogen, and percent oxygen. Suppose that we use the same experimental information that we had in the last problem, and the question, instead of saying what's the mass percent of each element, it said what's the empirical formula of this unknown compound, CXHYOZ. So what I've done is I've just copied down all the data that came from this last experiment. Here was a starting sample mass, 4.24 milligrams. Here it is in grams. Here's the mass of carbon that we found. Here's the mass of hydrogen that we found. And these were all the percent of each of these elements. So I want to find the empirical formula. And if you remember, if I have percentages or moles, if I have moles of each of these, I can put them into this balanced equation. So I want to find how many moles each of these things is. So the first thing we notice is I think I can find the moles of carbon because I have a mass of carbon, and I think I can find the moles of hydrogen because I have a mass of hydrogen. But how am I going to find that quantity Z? I'm going to need to figure out what the mass of oxygen is that I have. So here's the information I have. I found the mass of carbon, I found the mass of hydrogen, and I know the starting mass. So the oxygen, whatever the difference of the starting mass is, has to be due to oxygen because all the carbon got produced came from this starting sample, and all the hydrogen that got produced came from this starting sample. So whatever's left over has to be oxygen. So that's going to be the first thing I'm going to tackle. So the mass of oxygen is going to be equal to 4.24 times 10 to the minus 3 grams, that's my entire sample, minus the mass of carbon plus the mass of hydrogen. Or in other words, 4.24 times 10 to the minus 3 grams minus 1.69 times 10 to the minus 3 grams plus 2.85 times 10 to the minus 3 grams. And that equals to 2.27 times 10 to the minus 3 grams of oxygen. Okay, here's a good time to stop the video if you want to try to solve this yourself. We now have a mass of carbon, a mass of hydrogen, and a mass of oxygen. See if you can find the empirical formula. We did a problem like this earlier. You can pause the video and start and see if you can solve that problem. Okay, so we're gonna tackle this problem. We need to find the number of moles of carbon, hydrogen, and oxygen. Let's start with moles of carbon. 1.69 times 10 to the minus 3 grams carbon times 1 mole of carbon for every 12.01 grams of carbon. Grams cancels grams, and that's going to give me 1.41 times 10 to the minus 4 moles carbon. Likewise, moles hydrogen is going to equal to 2.85 times 10 to the minus 4 grams hydrogen times 1 mole of hydrogen for every 1.008 grams of hydrogen. That's going to cancel that, and that is going to give me 2.83 times 10 to the minus 4 moles of hydrogen. And now I'm going to use this mass of oxygen that I found to find the moles of oxygen. So the moles of oxygen is going to equal to 2.27 times 10 to the minus 3 grams oxygen times 1 mole of oxygen for every 16.00 grams of oxygen. Again, note, as in before, this is grams hydrogen, not H2. This is the mass of one oxygen, not O2. It's because we're dealing with one oxygen atom here, one hydrogen atom here. It's not molecular oxygen or molecular hydrogen. Okay, so grams oxygen will cancel grams oxygen, and this is going to equal to 1.42 times 10 to the minus 4. I've rounded with 3 sig figs at the end of each step, which is why we end up with these numbers. Okay, once we have moles, remember we can put this into our formula. And you notice also these are all times 10 to the minus 4, so I'm going to leave that off. I'm just going to say 1.41, H is 2.83, and oxygen is 1.42. Our trick to doing this is we look for the smallest number and divide each one by the same thing. In this case is 1.41. And if we go to 2 sig figs, this is going to be 1.0, H 2.0, and O 1.0. In other words, the empirical formula is CH2O for this unknown compound. Okay, so you can see how using combustion analysis we can find things like mass percent, we can find masses, or we could find something like the empirical formula. If we wanted to find the molecular formula, we need a little more information. We need like some mass spectroscopy data, which would tell us what the molecular formula was, formula mass was, and then we compare that to the empirical formula mass. My prior video showed you how to do that. So this is basically putting all the pieces together in the last couple of videos that we've had and to do the actual experiment, which is called the combustion analysis experiment. All right, thanks for watching.